Hello everyone, we are N11 and we are explaining floating point representation. Now going through the content slide, Introduction to Floating Point Representation, IEEE Standard 754 Floating Point Numbers. First, Single Precision IEEE 754 Floating Point Standard. Second, Double Precision IEEE 754 Floating Point Standard.
Floating point representation. Now the floating point is represented into three parts. The first part comes the sign part, the second one is the exponent, and the third one is the mantissa. You can also switch between the mantissa and exponent part, like first comes the sign part, then the mantissa, and then the exponent. Now first let's take an example. Now this is the final example where this first part is the sign part, the second part is the exponent part. This exponent part can also be written as 2 raised to 4 in the exponent form, where the base is 2 and exponent would be 4, and the third part comes as the mantissa. Now let's understand what are the three parts, what are their meanings, and with example understand them clearly. The first one is the sign part. The sign part shows the sign of the floating point, negative or positive, and it is determined by the most significant bit. Now here, as you can see in the example, the most significant bit of this example is 1. So therefore this would be the negative number, like 1 implies as the negative number and 0 implies as the positive number of the floating point representation. So when we consider the most significant bit of the example, it would be 1, and it would indicate the negative number. Now the second part here is the exponent part. Now exponent, this part is the sign part has the first bit in the binary representation. The next part, exponent part, has the 8 bits of the binary representation, and the next 23 bits remaining are for the mantissa part. Now first exponent part. In this part, 127 is the unique number for 32-bit floating point representation, where the case comes as bias. Now this condition is determined by condition like 2 raised to k minus 1 minus 1, where k is the number of bits in the exponent field. Now for the 8-bit representation, the k, or as you can see, the exponent is the 3. There are 3 exponents. For the 32-bit, this is the 8 exponent bits, and for 64-bit it is 10. Now to understand this more clearly, I'll give us example. Now the for bias, for 8-bit conversion, it would be, the representation would be 2 raised to 3 minus 1 is equal to that would be 4 minus 1, that is 3. So 3 for 8-bit conversion. Now 127 for 32-bit conversion. As previous, this would be 2 raised to 8 minus 1 minus 1. This would be 128 minus 1, that is 127. And similarly for 64-bit conversion, it would be 2 raised to 10 minus 1 minus 1, 1064 minus 1, 1063. That is 1063 for 64-bit conversion. Now here is the example. As you can see, this example is then converted into 131 into base 10. So 131 minus 127 is equal to 4. So hence the exponent of 2 will be 4, that is 2 raised to 4. So the exponent would be 16. So now the third part comes, the mantissa part, which consists of 23 bits of the binary representation. Now it consists of 1 and the fractional part, which is determined by the example. Now this is the example, and you can see the fractional part of the mantissa is given by 1 into 1 by 2 plus 0 into 1 by 4 plus 1 into 1 by 8 plus 0 into 1 by 16. Then this total would be and so on, and this would be 0.625. Thus the mantissa will be 1 plus 0.625, that would be 1.625. Thus the decimal number hence given as sign. The representation would be sign. First comes the sign part, then the exponent part, and then the mantissa, and that would be minus 1 into 0 into 16 into 1.625. This would be 26. Now there's another representation of this number where you switch between the sign and mantissa part. The mantissa would come first and the exponent would come second, and the sign, for minus 1 raised to 0, you could also consider 1, and that to if you don't do the sign part, it will be considered as positive number, and the exponent would be, you can also write it in the base to a power form, that would be 2 raised to 4. So the number would be as follow, 1.625 into 2 raised to 4, where the sign part is the 1, that would be the positive number that would indicate the negative number. Then the 2 raised to 4, 1.65, that is the mantissa, and the last one would be 2 raised to 4. The base would be 2 for the binary numbers, and for the decimal that same base would be 10. Huh.
So next slide is to convert the decimal into floating point. We have three elements in a 32 bits floating point representation. First is a sign, second is the exponent, and third is a mantissa. Sign bit. Sign bit is the first bit of the binary representation. One is implies a negative number and 0 is implies a positive number. Example, to convert minus 70 into 32 bits floating point representation, sign bit is equal to 1. Exponent is decided by the nearest smaller or equal to 2 raised to n numbers. For 1760 is the nearest 2 raised to n. Hence, the exponent of the 2 will be 4 since 2 raised to 4 is equal to 60. 127 is the unique number for 32-bit floating point representation. It is known as bias. It is determined by the 2 raised to k minus 1 where k is the number of bits in the exponent field. Thus bias is equal to 127 for 32 bits. In bracket 2 raised to 8 minus 1 is equal to 128 minus 1 is equal to 127. Now 127 plus 4 is equal to 131. That is 1 0 0 0 0 double 1 in a binary representation. Mantissa 70 in a binary is equal to 10001. Move the binary point so that there is only one bit from the left. Adjust the exponent of the 2 so that the value does not change. This is a normalizing the number 1.0001 2 raised to 4. Now consider the fractional part and represent it as 23 bits by adding 0. 0 0 1 as 70 times 0.
IEEE standard 754 floating point numbers. The IEEE standard for floating point arithmetic IEEE 754 is a technical standard for floating point computations which was established in 1985 by the Institute of Electrical and Electronics Engineers. The standard addressed many problems found in the diverse floating point implementations that made them difficult to use, reliable, and reduce their portability. IEEE standard 754 floating point is the most common representation today for real numbers on computers, including Intel-based PCs, Macs, and most unique platforms. There are several ways to represent floating point numbers, but IEEE 754 is the most efficient in most cases. IEEE 754 has three basic components. First is the biased exponent. The exponent field needs to represent both positive and negative exponent. A bias is added to the actual exponent in order to get the stored exponent. Second is the normalized mantissa. The mantissa is part of a number in scientific notation or floating point numbers consisting of its significant digits. Here we have only two digits, that is 0 and 1. So a normalized mantissa is one with only 1 to the left of the decimal. There are the two types, single precision and double precision. Sign first is 31st bit and second double precision is 63 bit. Biased exponent 8 of 30 minus 23 and double precision is 11 62 minus 52. Normalized demantissa 23 of 22 minus 0, 52 of 51 minus 0. Bias 127 1023.
So our basic aim is to represent a number into floating point representation. For that, basically convert that number into binary number and convert that binary number into 1 point something home. To find exponent, we have formula for single precision, that is e dash is equal to 127 plus e. Here the value of e is 6. So convert e dash into binary form. And to represent a number into floating point representation, the first digit represents the sign of that number, and then we represent the mantissa and then exponential. It is same for the double precision, but the formula for double precision is e dash is equal to 1023 plus e. Same procedure is to be followed in the double precision. First convert that number into binary form, then find exponential, that is e dash, by the formula of 1023 plus e. Convert that convert that number into binary, and to represent a number into floating point representation, first of all represent the sign of that number, then mantissa part, and then exponential part. Thank you.
Now we will convert it into double precision format. Here bias component precision will be 1023 plus 6, which is equal to 1029. Here 1023 is a biased for 64 bit. So 1029 represent 1 in binary form, 100000000101. And now normalized mantissa is same for 32-bit as well as for 64-bit is same, so it represents 0101010001. We will add zeros to complete the 52 bits. Therefore, the IEEE 754 double precision is 0 as a sign bit because 85.125 is a positive number, so we will take a 0, 100000000101 as an exponent bit, and 0101010001 till 52 bits we will be your mantissa. This is a representation of 85.125 in 64 bit. This can be written in the hexadecimal form 405548 till 10 zeros. Exponent will be depends upon bias, but mantissa will be same for both in single bias as well as double precision format. In single precision, we have to add 0 to complete 32 bits, and in double precision, we have to add 0 to complete 52 bits. Thank you. Please like and share.